Good morning or good afternoon, depending on where you're at. Very warm welcome to April 2026 monthly webinar at the IBT/ABC-UTC. My name is Atarod Azizi Namini, and I'm the director of the IBT/ABC-UTC. Title of the webinar this month is Exploring the Engineering Marvel of the Gordie Howe International Bridge. Very interesting topic. We are delighted to have with us Zahir Youssef, Chief Bridge Engineer and Vice President for the Engineering, Windsor Detroit Bridge Authority. Also Jonathan Vargas, also with the Senior Bridge Engineer with the Windsor Detroit Bridge Authority, and Kyle Copper, who is with the Michigan DOT, Chief Structural Design Engineer. So during the registration process, we did receive several questions. We are going to try to answer those questions. Before we start, first of all, we hope that all of you who have been enjoying this monthly webinar or other webinar activity like an in-depth or a research training seminars have marked your calendar to be with us. So we see you face to face on December 1st and 2nd for the 2026 World Bridge Engineering Conference that's going to be held at Hyatt Regency Hotel in Miami, Florida. Thanks to many state DOT that have co-sponsored this conference. Sponsor is U.S. Department of Transportation through our UTC. Registration is open. Please, by all means, if you plan to attend, please go ahead and register. There are opportunities to exhibit at the conference. There is an award program. There is also a travel scholarship program. So if you are a state or the county or a city agency, if you're a bridge owner and work for the government agencies at different level, you can apply in the US. You can apply for travel scholarship that pays your registration fee and the hotel and so on. So please consider that. At the request of, we have received tremendous amount of abstract, but many people were asking us to extend the time because of the project time limit and so on. So the absolute deadline for submitting the application for the abstract is May 25th. You can go online and submit your abstract. Like I said, travel scholarship is available. You can go on our website and apply for this travel scholarship. There is a award program associated with the conference, so we are going to give award at several different categories. Please visit our website and you can different categories where the awards will be given at the project level, at the individual level, and the procedure to submit your nominations. Also, day before the conference, this is a free event, all day long, non-destructive testing workshop. This is going to be very interesting. It's going to be half a day lecture by several different companies on different methods of the non-destructive testing. And then in the afternoon, there's going to be a hands-on opportunity for you to see the different non-destructive technology that you can apply to the bridge engineering. Also, in conjunction on the December 1st and 2nd, in conjunction with this conference, there is another event that is sponsored by the U.S. Department of Transportation, and that's the annual Transportation Infrastructure Summit. This is a very interesting, lots of universities are going to be involved in UTCs that are sponsored by the US DOT. So it's a very good opportunity for you to see not only the bridge engineering presentation and so on, but also other topics related to the transportation infrastructure. So at this point, I'm going to turn it to Kathy Kroll, who is going to share some additional news.
Thank you, Atorad. I'm Kathy Kroll. I'm a co-director of technology transfer for the IBT/ABC-UTC at Florida International University. I'd like to thank you and over 1,300 other registered participants for joining us for today's 181st webinar in our monthly webinar series. Before we get started, I'd like to share a few announcements with you from the industry. The AISC NSBA's 2026 Steel Conference is next week. It will be held April 22nd through the 24th in Atlanta, Georgia. The 4th International Interactive Symposium on UHPC will be held in Des Moines, Iowa, June 14th through the 17th. For anyone interested in UHPC, this is a very valuable conference. Put it on your calendars. The Engineers Society of Western Pennsylvania will be presenting the International Bridge Conference, the IBC, from June 15th to the 17th in National Harbor, Maryland. ASHTO's Committee on Bridges and Structures meeting will be held June 28th through July 2nd in Charlotte, North Carolina. Continuing to our own events, next Friday, April 24th, we will be holding our quarterly research seminar from 1 to 2:15 Eastern. The featured projects will be a comprehensive formulation prioritizing bridge intervention subject to flood hazards. Our colleagues from FAMU FSU will be presenting. Registration is open. Sign up now. Our next monthly webinar will be on Thursday, May 21st from 1 to 2:15 Eastern. The presentation will be about the Fern Hollow Bridge collapse in Pittsburgh and how the city overhauled their bridge asset management program in response. Pittsburgh's Chief City Engineer, Eric Setzler, and WSP's Lou Ruzzi will be presenting. Registration is open. That's all for our announcements, but on to our standard housekeeping items. As many of you may know, these webinars are recorded and posted on the IBT-ABC-UTC website in the section titled Monthly Webinar Archives. So you can access this and all previous webinars for future learning and to share with interested colleagues. I'd also like to point out that a PDF version of today's presentation posted in the archives. Lastly, this presentation will be followed by a question and answer session. With that, we'll begin our feature presentation. We are happy to welcome our presenters, Zahir Yusuf and Jonathan Keano from the Windsor-Detroit Bridge Authority, and Kyle Copper with WSP, formerly with the Michigan DOT. Thank you all for joining us to share information about this landmark project. Zahir will get us started.
Thank you very much, Kathy, and thank you very much, everyone, for joining us. As mentioned, my name is Zahir Yusuf. I am the Chief Bridge Engineer and Vice President of Engineering. We'll be joining, as I mentioned, by my colleague, Jonathan and Kyle. So the Gordie Howe International Bridge Project represents one of the most exciting international infrastructure initiative currently in progress at the end of the construction. I will be discussing initially during the presentation the project overview, the organizational framework for the project, as well as the design specification and the technical requirements for the bridge. Jonathan and Kyle will cover the construction sequence of several major structure components of the bridge, including foundation, footing, the bridge deck, and the superstructure. We often been asked why we need a new bridge between Windsor and Detroit. The Windsor-Detroit Gateway is the busiest commercial land border crossing on the Canadian-US border, with over 1/4 of the total bilateral trade crossing over the Detroit. Nearly $1 trillion worth of commerce crossed the Canada-US border in 2022, with over 7,000 trucks crossing daily here in Windsor-Detroit. More than 250,000 jobs in Michigan depends on the trade and investments, and approximately 6,000 workers cross at Windsor-Detroit every day to work on the other side of the border. Currently, there is an existing bridge between Windsor and Detroit. That bridge is built in 1929. It's carried 2 lanes in each direction. So therefore, the new Gordie Howe International Bridge addresses key regional transportation needs that support the efficient and effectiveness movement of people and goods through the Windsor-Detroit Gateway, which provide redundancy, improve border crossing and then capacity for current and future traffic volume. Our bridge will have 3 lanes in each direction, and then it's built to the latest standards. Also, the Gordie Howe International Bridge will provide highway-to-highway connectivity between Windsor and Detroit. So there will be no traffic going through both downtowns, Detroit and Windsor. This image illustrates the project organization structure with WDBA partner and oversight bodies. Windsor-Detroit Bridge Authority is the non-profit Canadian Crown Corporation charged with a mandate to deliver the Gordie Howe International Bridge between Windsor and Detroit through a public-private partnership, or P3. Our mandate, our WDBA, is overseen by a board of directors. Also, we have the International Authority, which is a joint Canada-Michigan governance entity, was established to oversee and approve key steps in the P3 procurement process for the new Windsor-Detroit Bridge crossing. In September 2018, WDBA selected Bridging North America as its private sector partner to design, build, operate, finance, and maintain the project. It is important to note that even though we have a private sector partner, WDBA continue to play a significant role in delivery of the project with our partners, Michigan Department of Transportation. Our private partner, Bridge North America, comprised of companies such as Dragados, Fluor, Aecon, and the lead designer is Aecon. Before we begin, I'll do some quick context setting to get you familiarized with the project and give you a lay of lands for when we are out on site. Valued at $6.4 billion, the project includes the delivery of 4 major components: the bridge, Canadian and U.S. port of entry, as well as the connection into the Michigan interstate system. As you can see on the right of the slide, there is the Canadian port of entry connected to Highway 401, and then the cable stay bridge crossing the Detroit River, and the U.S. port of entry on the Detroit side, and then the connection to interstate. These are some rendering shows the 4 components of the project. As I mentioned, the bridge, the 2 ports of entries, and the Michigan interstate. Each of these 4 components are significant in their own scope and complexity. However, the focus of this presentation will be on the cable stay bridge. An interesting aspect of the project is the environmental and sustainability considerations that have been incorporated. The Gordie Howe International Bridge project is an example of sustainable infrastructure that contribute to a clear environment, protect communities from impacts of climate change, and conserve resources for future generations. Among numerous features, some of the key examples of sustainable design integrated into the project include, these are only few, the LED lighting for exterior lighting and in POE buildings, port of entry building designed to take advantage of natural lights, water management system to reduce water demand, and integration of even the pavement piping boxes into the bridge design. The cable stay bridge will have 6 lanes, 3 Canadian bond and 3 US bond, and a clear span of half mile with no pier in the water. The bridge is built for 125-year service life. The main tower, approximately 722 feet. The total length of the bridge from the abutment to abutment, including the both approaches on the US and Canada, is 1.5 miles. The main span, as I mentioned, is half mile, 2,800 feet roughly, between the tower, and therefore the bridge is considered the longest cable stay span in North America and the 10th in the world. This is also the world's longest, if you composite deck cable stay bridge for the type of the deck. The approach bridges consist of 9 spans on the Canadian side and 9 spans on the US side. There will be more discussion in detail about the substructure, but briefly, the tower and the pier are formed in reinforced concrete. The superstructure for the main bridge is a steel girder with a full depth precast concrete deck. Approach pier consists of steel curved girder with cast in place deck. A 125 service life must be demand. That was and the bridge is built for that, for non-replaceable elements. We will discuss more in detail the foundation. As construction is near completion, now we are in the process of commissioning, final commissioning and testing. In addition to being the longest cable stay bridge in North America and the 10th longest in the world, Gordie Howe International Bridge will include features that specifically created to commercial traffic. The bridge will include lanes that measure 12.1 feet wide with an extra wide lane to accommodate oversized vehicles. Additionally, the multi-use path for pedestrian and cyclists is separated from the vehicular traffic with barriers, and that separation continues throughout the entire footprint. Now we'll go into greater detail about the design features of the Gordie Howe International Bridge. This is the bridge superstructure elevation view, and it shows the navigation channel envelope for the Detroit River, which is roughly around 2,500 feet times 137 feet. The maximum under bridge clearance, we met the clearance of 138 feet in the center span. US side span is around 1,171 feet, and the Canadian side is around 1,155 feet. We have 2 side span piers, as you can see on both sides, and 1 anchor pier at the end of the back span of the cable stay bridge. Superstructure for the entire cable stay bridge is a steel with post-tension precast. Steel used in the bridge was sourced from both Canada and the United States, only under the by Can-Am provisions of the project agreement. This is an image of the bridge superstructure deck. The maximum superstructure depth is 10 feet. The superstructure is a closed box with a soffit panel at the bottom and concrete deck slab on top, and it's comprised of two 8-feet edge girder on the side, three internal longitudinal girder, and multiple floor beams at 6.4 feet spacing from anchor pier to anchor pier, which connecting the two edge girder on the side. The deck thickness is 10 inches, including 0.4-inch sacrificial top surface thickness. 2-inch of latex modified concrete was used as a surface overlay. The precast deck panel are post tensions in both directions and use around 10,000 psi of concrete. The deck is designed as a zero tension limit in the service limit state that was required to improve durability and service life. Also, in terms of the structural design feature, the main towers are in the inverted Y configuration with two planes of cable connecting to the exterior of the deck. As I mentioned, the tower and substructures all are built with reinforced concrete. The tower were constructed on the area with limestone rock located roughly around 100 feet below the existing ground. The foundation depth for each of the tower leg roughly is 25 feet with a regular shape, as you can see in the drawing. The foundation type used is a drill shaft around 10 feet in diameter. There were 6 drill shafts for each side of the leg for each tower. And those foundations, they were rock socketed approximately 20 feet. An interesting aspect of the project is that the main bridge will be a dual track design, meeting the requirements of both Canadian CSC S6 and the AASHTO load resisting factor design. This will guarantee the design will comply with the applicable design codes on both sides of the border. The dual design refers to two complete design sets done by the engineer of record, two complete set of calculations using the Canada track and US track, using the Canadian and common bridge design standards in international system of units. And second design documented with a complete set of design calculation will be using the US and common bridge design standards in English units. The design plan shall meet the minimum requirements on both Canada track and US track. Because of the span of this bridge, a deviation from the national bridge design codes were limited by focusing to adjacent to the national live load model. Adjustments were made based on simulation study using weigh-in-motion data provided by Michigan Department of Transportation, as you can see it on the left side of this slide, and the Ontario Ministry of Transportation on the right side. The US weigh-in-motion data consists of around 700,000 truck records collected from 4 interstate highway sites around the southeast Michigan by MDOT in between 2011 to 2013 timeframe. The low end of the data was defined by filter enforcing a lower gross vehicle limit to 9 kips for a 2-axle and 12 kips for 3-axle truck of the high end. The data was known to include a special permit load as large as 280 kips, as you can see in the graph. The Canadian data on the right side is from 2012 Ontario Commercial Vehicle Surveyor, and includes about 20,000 records from Southern Ontario. The maximum truck weight presented in the CVS data used in the load study was 180 kips. 2 sets of normal traffic live load were used for the design based on the live load study on each of the design procedure following the Canadian and US calculation. The following set of normal traffic live load are substituted for normal traffic live load in the Canadian and AASHTO codes. The intensity of the distributed live lane load was reviewed. The design track is the same both for commercial vehicle lane and mixed use lane. For Canadian design calculation, the modified loading will be considered. The truck used will be CL625 on this is the standards on truck used by Canadian Highway Bridge Design Codes. The HL93 truck from AASHTO LRT were modified to what we call a WGBA AASHTO truck as shown on the right side and was modified to become 5-axle loads. In addition to the live load study, a special loading design was considered for this crossing. The area goes through multiple parades and marathons. Therefore, we want the designer to consider that in the design. The thermal gradient loadings was also required. Site-specific seismic design using lifeline, irregular critical structure. These are the term, I put all the term used based on AASHTO and the Canadian. They are the same thing, but use different terms. Even we didn't have any infrastructure in the river, and the piers are located in the land adjacent to the seawall or embankment on both sides. We wanted the designer to consider the vessel collision impact on the seawall, and if there is any impact through the soil into the foundation of the tower. And the snow load also was considered due to the length of the bridge. To meet the service life of 125 years, the requirements were specific on some of the specific criteria in addition of the durability analysis. Stainless steel reinforcement was used in the bridge deck and the precast. Structural steel was allow to the designer to use one of these. They ended with using the A709. All structural steel, including weathering steel, if used, shall be coated. Requirements for the service life. And reinforced steel used in the bridge was the grade 400W. Also, the technical requirements allow the designer to select different type of reinforcement, but was mainly what was used in stainless steel when it's specifically required, or by the technical requirements or by durability plan preparer and designer. They use some of the typical low carbon steel. Parallel strand system is composed of individually sheathed and filled with 7 wire strands encased in the outer excluded high density polythene, or HDPE, and are 0.62 inch in diameter and have cross-sectional area of 0.23 square inches. The approximate forces on the cable will vary between 770 kips to 2,800 kips, depending on the cable location and length. Number of strands, we had 216 parallel strand cable used on the bridge. The number of strands vary depending on the cable from 38 strands to 122 strands. I mentioned the service life and design life. These are the service life requirements that was considered for the project in 3 steps of the project. During the design, the concrete cover, concrete mix requirements, steel detailing and coating, and the similar matter were need to be considered in the design. During construction, the means and method, we wanted those means and method to be selected and consider the service life requirements. Very stringent QA/QC requirements was identified by the agreement for the contractor to follow. And also, because it's a P3 project, we wanted that also to be considered during the operation, as our private partner will be responsible for maintaining the bridge for 30 years term. As I mentioned earlier, the bridge is the longest in the world, utilizing the composite steel superstructure with concrete deck. This represents a step forward for the bridge and therefore approve of aerodynamic performance, a key consideration in the section of the design. Wind culling tests for complete structure and for the bridge under construction were conducted at RWDI facilities in Guelph, Ontario. These are one of the facilities, which they are the largest facilities in North America for this kind of signature and significant project. Requirements for the test were: the bridge shall not exhibit aeroelastic instability during construction phase for a wind velocity having a return period of 1,000 years. That's during construction. The bridge also shall not exhibit aeroelastic instability, flatter, or galloping in service for wind velocity having a return period of 10,000 years. That's in the operation phase. The bridge is aerodynamically stable in wind beyond 1 in 10,000 years, which assessed to be a wind speed of 108 miles per hour. That was the first model, which is the sectional model. This test investigates the stability against flatter vortex shedding, induced motion, and response to buffeting wind direction stage. The geometric scale of the model was 1 in 265. The test was carried out using a full-scale 10-minute mean wind speed range of at least 32.8 feet per second to 230 feet per second. If you're familiar with meter per second, 10 meter per second to 17 meter per second, or in mile, 156 mile per hour. The test also was carried out with heavy high side vehicle traffic on the main bridge because it's very busy crossing. So sometimes there will be commercial vehicles packed from one end to the other end of the bridge. So the wind model considered that. The second model was the testing the aeroelastic model for the bridge with a full one scale, with a scale of 1 into 230. This model was tested in a stage of construction and also in the full bridge constructed as a full under operation. Other model is the tower. The tower was tested as a freestanding, as you know, because of the way these bridges are constructed. The tower will be built prior at a certain stage a certain length prior to be cable to be connected to the deck and to the tower. Therefore, we wanted the tower as well to be tested, including the tower crane, as you can see it's in the model, to be tested as a freestanding. For the surface overlay, the contractor used the lattice modified concrete 2-inch thick, and that was used for the travel lane and also for the multi-use path. Some of the challenges in the design and construction, I think designing a bridge between two nations is you need to meet the requirements of the two nations. Sometimes there are different standards. Therefore, the requirements were to design for both standards and use the most stringent from the analysis two standards and use it in the construction. During construction, construction started in 2018, and as you know, we had the COVID. Although we have some of the large elements of the projects, because of the size of the elements, the contractor was able to, in some cases, able to mitigate some of the work because they can be able to allow space between workers to do some work. But there was an impact from COVID. There are some challenges in the area from the weather condition here and high wind, and some of the other challenges is because we have the two sides of the bridge built on cities, Windsor and Detroit. There were some challenges dealing with the private utilities and public utilities. There were advanced work to relocate some of the private and public utilities, but there's still also some of the utilities need to be relocated during construction. And also we wanted to meet the requirements of the municipality at both sides, and it was required a lot of coordination and discussion between the two city municipalities so that they will be accepting what we will be building. Some of the lesson learned from this one is this kind of projects, P3, establishing a communication protocol at the early of the project, it's very essential. Maintaining open communication at every phase of the project to address contractual issues and maintain cost and schedule. As you saw from the slides, we have multiple stakeholders on both sides of the border, ensuring the necessary authority and contractual requirements are established for components that may be fully encompassed by design, build, finance, operates, and maintains model. Documentations, it's very important that having complete documentation at the early stage of the project will help in the end stage of the project when you try to close the project. And then again, the collaboration among the internal teams as well, that's something need to be focused on. With that, I will turn it over to my colleague, Jonathan Keano, to continue the presentation. Thank you so much.
Thank you, Zahir, for that section of the presentation. We will now be getting into bridge construction update, and we will be basically touching on some of major structural components of the bridge and what took essentially to accomplish this major engineering feature. So the picture you're seeing now is of the main span and the joining of the deck, which we will get into later on in the presentation. Okay, so starting with the bridge foundations, a structure this size requires a strong foundation, especially one that is going to support the longest main span of any cable stay bridge in North America. The foundation for each tower in Canada and the US is composed of a total of 118-foot drill production shafts. So there's 12 for the main footing and 6 for the backspan. Each tower footing is composed of a total of 67,450 cubic feet of concrete, approximately 970,000 pounds of rebar, and more than 5,250 feet of post-station cables. A sacrificial steel shell was installed with the drill shafts based on site-specific soil and water corrosivity data. To give a sense of the magnitude of this work, the first 3 concrete pours required on one footing took upwards of 24 hours and 2 separate work crews of nearly 50 people. And in the pictures, you can see basically the density of the reinforcement for this drill shaft was quite high. Moving on, foundations, the drill shafts, as I mentioned, are connected to the bridge tower footings. So the foundation work was completed in 2020. It included 9.8 feet diameter drill shafts, as I mentioned, 12 per tower, and they contain approximately 1,700 tons of reinforcing steel. Construction of the footings began shortly thereafter and were completed in July 2021. For the first pour alone, we used approximately 35,000 cubic feet of concrete, and the footings used 6,000 psi concrete. Upon completion, the footings total a combined of 268,000 cubic feet, or what would be the equivalent of 2 million gallons of concrete, and approximately 1,900 tons of reinforcing steel. And additional to that, there were 240 tons of reinforcing steel in the tie beams. The tie beam is essentially part of the footing of the foundations that connects the two footings. And what it does is, the purpose of this element is basically to resist lateral forces that will be transferred onto the footings. This tie beam is post tension using 25 ducts, which house 31 strand tendons, and they are post tension, as I mentioned. So following the construction of the footings, construction of the main tower legs started. As you can see from the pictures, there was some flexibility or liberty, to put it that way, for some design art on the US and the Canadian side. So on the US side, you'll see they use the blue collar jump forms, and on the Canadian side, they had different art representing basically the Canadian culture. So the tower construction is broken into three pieces: the tower legs, the upper cross beams, and the tower head. Each tower has a north and south leg that meet at the upper cross beam before joining the tower head above. Installation of the climbing formwork system used in the construction of the tower legs began in January 2021. Each one of the 29 concrete lifts for each north and south leg tower contained approximately 3,500 to 9,500 cubic feet of concrete, totaling approximately 388,000 cubic feet. The density of the reinforcing steel in each tower lift was approximately 34 pounds per cubic feet. Most of the steel was pre-assembled in jigs on the ground and then lifted in place on the tower leg and tied together. Following the overall construction approach that was used on the main span of the bridge that extended over the Detroit River is used a technique called unbalanced cantilever or stick build. Starting from the main towers in Windsor and Detroit, construction of the bridge started outwards from the center. So I will explain with the pointer. So this, when I say backspan, I'm referring to these areas on the land. So this is the main waterway. So construction of the deck started from the backspan using these temporary bands or temporary piers, which were used to support this section of the concrete deck. These three piers are the permanent piers, with the last one being the anchor pier. The term cantilever in construction typically refers to a balanced approach with the same level of construction occurring on each side of the tower, but in the case of the Gordie Howe Bridge, it was constructed in an unbalanced fashion, with the backspan of the bridge road deck being constructed first and the temporary supports being removed once the stay cables were installed and construction of the main span began. Construction materials and equipment were transported over the backspan to the construction zone once the main span construction started, and these activities were taken on the bridge deck, eliminating the need for equipment to operate from the water. Okay, so with this information, I will pass it on to Kyle Copper to continue the presentation.
Thanks, Jonathan. Appreciate it. So one of the most important lessons I learned from being part of this project was the importance of planning and preparation when taking on a design or construction challenge. I had a college professor who used to preach, plan your work, then work your plan. And being part of this job made me realize that this mantra was even more critical the more complex a project was. And I think you've started to see some of that with the information that Zahar and Jonathan have presented. As Jonathan mentioned, the back spans were constructed prior to the main span being built, and to facilitate that work, they were supported on temporary piers. So in the bottom left corner there, you can see a picture of the back span shortly after construction started, being supported by those temporary piers. Each of those temporary piers were constructed from about 4-foot diameter steel that had 1-inch wall thickness, and the height of those piers ranged from 72 feet up to 118 feet as you got closer to the towers. Each column of the temporary pier was founded on steel H-piles, and there was a double steel I-beam section at the top to support the superstructure. The bridge approaches. The main bridge is connected to the ports of entry by a series of approach spans. There are 9 approach spans on each side of the main bridge, and in those 9, each of those 9 spans, there's 10 girder lines. All told, there's approximately 6,000 tons of structural steel that was required to construct the approach spans. The decks on the approach spans are cast in place concrete, reinforced with stainless steel reinforcement. So here on the screen, the picture on the left side shows the U.S. approach span under construction, and the picture on the right side shows the superstructure in one of the Canadian approach spans. Going back to the tower anchor, the tower head, to help facilitate the construction of the tower head and to transfer the forces from each of the stay cables to the bridge, anchor boxes were utilized. In each tower head, there are a total of 27 anchor boxes, and those are in addition to 8 permanent boxes that were used strictly for forms. So you can see on the very left side of this slide, one of those anchor boxes. On the face here, you can see the guide pipes that the stay cables will extend through into the tower head. In the middle of the screen, you can see a cross section that shows the cast in place concrete on the left side. This blue line right here is the wall of the anchor box. And then inside is open to provide access for not only construction, but also inspection and maintenance once the bridge is in service. So you can see the stay cable coming through. And then right here is the anchor beam. And on the top of the anchor beam is an anchor plate, and all the stressing that was done for the stay cables was done in the tower. The reaction goes through the beam into the walls and gets transferred through these shear studs into the cast in place concrete that was added for the tower head. So the US tower reached its final height of 722 feet in August of 2023. The Canadian tower was completed a little bit later in December of the same year. Here's a few pictures showing the completed tower. The main span deck construction, very complex operation. A lot of planning went into it. The 2 cantilevers stretched out from the towers almost a quarter mile and reached the middle or the mid-span segment in June of 2024. And so before all the final pieces could be set in, there were a lot of temporary braces and jacks that were installed in between the 2 leading edges of the cantilever to help the contractor control vertical alignment, horizontal alignment, as well as racking and things like that to make sure that they could get the final pieces set in place. So the operation to install the final pieces of the edge girder took place on June 14th of 2024. Operation started very, very early in the morning, which allowed the contractor to have a little bit more control and not to be impacted by the thermal forces from the steel heating up in the daylight, in the sunshine during the daylight. The operation went very smoothly with the pieces coming within a couple inches of each other, which required a little bit of adjustment, but a very successful operation and in no small part to all the planning and preparation that the contractor and the engineer did to get to that point. Just real quick, a few more things about the stay cables. So as Zahar had mentioned earlier, there's 216 of them on the bridge. There is anywhere from 38 to 122 strands in there. And if you place the unstressed strands end to end, there would be almost 3,000 miles of it that was used in the project. And just to give some perspective, if you set them end to end, that would take you from the Gordie Howe project location all the way to Anchorage, Alaska. So if you want to stay in touch and keep up on the progress of the project, here's some ways you can do that. We wanted to show a video of the mid-span closure, but unfortunately because of time, we weren't able to, but a link to that video has been posted to the FIU website, or you can go to WDBA's YouTube page and find not only that video, but literally hundreds of videos showing not only construction of the project, but interviews with different people who were involved in the project, and really great way to see all the hard work that went into it. And with that concludes our presentation.
Thank you to our speaker. Wonderful presentation. We have received lots of questions. We are going to turn it to Paul Lyles.
Okay, thank you, Tori. We have some questions that came in early before the webinar, and I'll start off with those, and we'll get into some that came in during the webinar, and there'll be more coming in during the Q&A, I think. The first one I have here is, was any specialized heavy equipment needed for this project?
And I think because of the size of the, as you guys noticed, the size of the tower, the height of the tower, the spans, the width of the bridge, there was some heavy equipments like the very heavy crawl crane used, the tower cranes reaching to that height. So this can be considered building elevator within the tower to reaching to that height, pushing concrete to that height of the tower. So I can consider everything was quite significant use for this because of the size of the project of the bridge.
Okay, here's another question that came in. This came in beforehand, but also from a number of people during the presentation. They asked about freezing rain and ice falling from the cables during winter. Is there anything to provide protection, or what's the plan there?
So the bridge components, the tower and the cable, were designed to mitigate the risk of ice falling and packed of snow, build of snow. So the cable, they were built in a way that to minimize the buildup of snow on the cable itself, with having those helicine around the rings around the cable. If you notice from the picture, there are some kind of round things spaced along the cable, and the tower shape itself also was built in a way to minimize the buildup of the ice and snow falling. So that was an additional to the weathering system and monitoring and alert. That was the passive system built for the mitigate the snow falling. It's not an active system, it's a passive system.
Okay. Question came in earlier about how many engineers worked on the design of the bridge?
A very large number. I don't have the large number, but the only thing I can say that the offices that were involved in the design, from the design firm, they were scattered across North America, multiple offices, even in Europe and in Asia. There was offices in Hong Kong involved. There was offices in Europe also. They were involved in the design. And the independent design checker also, they had some different locations in North America and Europe.
Okay. What geotechnical tests were important on this project?
For the foundations, they carried out the overstring test, which basically is a test that is done on structures where there is a limitation on space. And this was done essentially to prove basically that the capacity of the foundation shafts. So this was done for the foundations, and many other components of the bridge saw basically mock-ups, which were a requirement of project agreement, so that basically there was a chance to verify things such as the finished surface of the concrete and basically durability and the capacity of several structural elements for the bridge.
Okay. I know you mentioned the Osterberg cell that you did in the, I think you'd said the demonstration shaft earlier, but then did y'all use cross-hole sonic logging to verify the integrity of the shafts?
That was done.
Okay, good. What was the timeline from conceptual design to completion of the project?
As I mentioned, the project was awarded in 2018. And this P3 contract, they started with the procurement phase RFP, when the contractor provide a concept design as a part of the RFP phase that considered concept design. And then after the award, they will develop that design. After the award, which started in 2018, they developed it to a final design. And the design was going through multiple steps: concept design, stage 1, stage 2, and then sign seal drawing. So, and because of the way this contract P3 goes, the design and construction goes in parallel. So basically the design will continue while the construction also is going. Every time they finish the design for the substructure, construction will start. And we are now at the final construction. The design was completed in last year with some minor changes, and anything normally will come. So that's the way this kind of projects goes.
Okay. Were there any challenges on the project associated with the accidental mixing of metric and imperial units?
I think if you guys noticed from one of the slides, I mentioned the dual design. And then we consider that during the development of the project agreements that because of they use different metric. So therefore we requested to have two designs, one in using each unit, and the designer will use in his final plan stringent requirements from those design and use one unit for the plan which will be issued to the construction. So the plan which was issued for construction, it was in single units, not the both units, but the design was considerable. Any issues so for as far as connection or any survey issue from that.
Okay. What is the P3, this public-private partnership agreement for future maintenance?
So our private partner that's why our contract is design, build, finance, operate, and maintain. So we have a contract with them to design, build, finance, operate, and maintain for 30-year terms after substantial completion. They are responsible for maintaining the assets, and then there are requirements for the handback requirements for these assets after the term, which is 30 years.
Okay. Who does the load rating and bridge inspection for this bridge? And will the load rating will it be accomplished in metric or imperial units or both?
So the requirements, it's from the designer to provide during the DB phase, design build phase, to provide load rating reports. Load rating reports will use the AASHTO standards for load rating. And during the operation, any oversized vehicle will be our private partner will evaluate those oversized overload vehicles based on that designer provided load rating. As I think there's one more. The inspection of the bridge the bridge is constructed as part of the national highway, so okay. The requirements of that will apply to our bridge.
How about the annual inspections all during the life of it? Who's going to do that?
That's the contractor will hire accredited consultants to do the inspections and to meet the requirements of as I mentioned, the requirements based on the national highway system on both from the US side and on the Canadian side. And the bridge, by the way, the steel girders is designed as a system redundancy member as per the AASHTO requirements.
Okay. Do you have any specific recommendations or best practices for working on projects that are affected by international and maybe state-to-state borders? You had a pretty good slide on it. I don't know if you want to add anything to it.
Yeah, I mentioned that the early coordinations was important. Sometimes you have one of the sides not familiar with the model of the project. Depending on what type of your project is it P3, is it only design build? So having a discussion with both sides and see what they are experienced with and try to have early discussion with them, educating them about the type of the project and the requirements, that will help a lot actually.
Okay, was lightweight fill used on this project at all?
For the main bridge, there was lightweight fill, and then on a lot of the bridges in the interchange as well, it was used. The soils in Detroit have been described as toothpaste, and you could stand out there and watch a 80-foot tall H-pile just sink under its own weight. So there was definitely a need to make sure we were being smart about, or the designer, was being smart about how much load was being applied to the soils.
Okay. Was lightweight concrete used at all?
No.
Okay, that's fine. Is the construction work on the Michigan DOT approach fully constructed now? Is it still going on?
Yeah, it's essentially done. There's some punch list items and some things that need to be addressed before meeting substantial completion, but all the infrastructure is more or less complete on the interchange.
Can you comment on why a cable stayed bridge was chosen over a suspension bridge?
Actually, in the project agreement for the shortlisted proponents during the procurement phase, we identify two options, the suspension bridge and the cable stay bridge. And we don't want them to go through because we don't want any infrastructure in the river. So, and our private partner selected, because it's design, build, finance, and competitive process, he selected the cable stay option.
Okay. Did you consider maybe any FRP composites for the bridge?
I don't think they use any for the bridge itself. If they use it in some of these elements on the buildings or equipment, maybe, but for the bridge itself, there was no FRP use.
Okay. Do you have any interesting engineering-related fun fact about the Gordie Howe Bridge and its construction?
The aesthetic of the bridge is because of the name of the bridge. I don't know if people are familiar. Gordie Howe is a hockey player. He's a Canadian hockey player. He played for Detroit Wings for many years, well known on both sides of the border here. And architectural aesthetic people are trying to mimic some of these things, and you can see some of the shape of the tower as a hockey stick, some of the geometry of that. So I think that was something to look at. I think there was a picture on showing the Gordie Howe holding a stick on both sides. If you put the mirror image, you can see it'll give you the shape of the tower.
Okay. How are the steel strands inspected since they're enclosed in HDPE pipe?
So there are some sensors and corrosion resistance requirements installed, and also we have a requirement to inspect the cables. Now there is option about robotic inspections, and this one of the cable along the cable inspects the HDPE pipe itself, and the strand. There are some monitoring devices as well installed.
Okay. There was a question about the tensile stress limits for the deck. You mentioned 0, though. You want to comment on that?
The requirement was because of durability and service life, and we don't want, because of how important is this crossing for the trade, we don't want interruption on the replacement of the decks often. And I think for the service life, the bridge deck is designed for 0 tension. That was one of the requirements for under service limit states. That will be 0 tension. Therefore, there are post-tensioning strands in both directions in some of the critical areas across the bridge itself.
Okay. Question, it says, was the superstructure designed to meet AASHTO SRM and or IRM, the AASHTO guide spec? And SRM is system redundant members and IRM is internally redundant members. That came around 2018. That's a guide spec. Did y'all use that?
We follow the SRM. Therefore, the edge girder, the steel girder, as designated as SRM. The intention was to minimize the hands-on inspections. If you designate the bridge, the steel girder were fabricated as fracture control and under stringent requirements of the D1.5.
Okay. What coating was used on the weathering steel?
There were 3 types, and I don't recall the 3 system coating used. I can provide the name of that later.
Okay. How were dissimilar metals and straight currents handled in design? Were they isolated or bonded and grounded?
We had the grounding on the towers. Definitely, there was on the foundation area on the land. There were requirements for dissimilar between galvanized because the deck was stainless steel and some of the elements of the bridge were normal steel. So there are requirements to mitigate any dissimilar contacts across the bridge. Lake currents, we didn't have any things. As you can see, we don't have any LRT or anything around that. So.
All right. Which codes were used for vessel collision analysis?
Both codes, actually. We want them to analyze both codes using the AASHTO LRD and then also the Canadian Highway Bridge Design Code. Both codes, they have sections for designing for vessel. What we did, we specify by the loads of the vessel to be considered and the degree of the impact on the seawall embankments adjacent to the tower.
Okay. Are the stays jacked from one end only?
They are jacked from the deck level.
Okay.
Only.
Do you have any idea for the average duration of erection per segment?
As typical, there was some learning curve in the beginning, as started with 2 weeks, because as you notice from Jonathan's sketch, it was assembled with placing the edge girders and then connected with the floor beam and then the 3 longitudinal girders for each segment. The cycle of this ones vary in the beginning, sometimes 2 to 3 weeks, and then later they were going very, very quick with less than that.
Okay. Who supplied the anchorage system, and did y'all do the cyclic fatigue testing on the anchorage?
The DSI, the DVDAC, DSI, I'm sure people are familiar with DVDAC, DSI. On the U.S. side, they supply the cable system and the strands, and then yes, they comply with all the fatigue requirements, design requirements.
Okay, I'm going to ask Rick to come on and pick up, and he'll get you some more questions. Rick.
Yeah. Thanks, Paul. So yeah, there's a lot of questions here. Yeah, one question that I thought was interesting that I came in was in the deck, the cast in place deck used stainless steel. Was there a reason hot dip galvanized epoxy or something like that wasn't used for that reinforcement?
It's just the service life. We want to minimize the closure of this crossing. How important is this crossing for trade? So we wanted to go extreme in minimizing the maintenance and rehabilitation and replacement. That was the reason.
Okay. During the, obviously there are lots of erection stuff going on. There was a model beforehand. How did the model match up to what you actually experienced as far as the deformation and, you know, getting everything to come together as the bridge progressed?
When you say the model, is you are referring to the wind load?
Yeah, or the analytical model. I'm assuming we had an analytical model somewhere for it.
Yeah, there was wind analysis report provided by RWI to the designer and consider in the erection and this. And this kind of bridges with the cable stay with this span, there is always fine tuning during the construction or stressing of the cable. So there are some adjustments on the forces on the strands on the cables from during the construction, as typically this is happened for this kind of bridges.
Okay. So I think one of the pictures Kyle had there showed the final stage, you know, the closure in the middle. And funny question here. Who did the actual work on the final closure? Did the Canadian crew or the U.S. crew, or did they work together to do that final push there?
Actually, both U.S. crew, they started from U.S. side and Canadian. And you can see the two tower cranes on the picture below. And then they met in the middle. So, and we have very nice picture of the iron workers from U.S. with iron workers from Canada. At the time of they connected this with shake hands between the two sides. Unfortunately, I didn't prepare that picture. That was very nice picture showing the flags from both sides and the iron workers standing on one side and the other side, and they shake hands.
Ice, snow on the cables, on the towers. What were accommodations to make sure to kind of prevent that stuff from falling into traffic during winter conditions?
As I mentioned, we did what we call it passive. The passive normally you do based on, you provide geometry, which is the shape of the cable on the top of the cable, the slope to prevent buildup of the snow on the tower, itself, the shape of the tower. And the cable itself, if you zoom in on the cable, you can see there are around 1 foot space. There is a rings welded to the cable to minimize the buildup of the snow and minimize that. That's what we call it passive system for minimize. And also there are the weathering system, the alert, the monitoring, which is connected. We have 2 weathering stations on top of the tower connected to our traffic management system.
Oh, the towers, I think Kyle showed a picture of the embed in the tower itself, but I'm assuming the center, somebody was asking about the center, you know, is it hollow where it can facilitate inspection and stuff? That was, and then I guess it rolls into the inspection of all the cables and everything. I mean, is there certain access that was established to be able to get to doing all the inspection? I know in one of the cross sections of the superstructure, you show there's manhole, or, you know, there's access where somebody can walk clear through. I mean, I think climbing through it. So it was, you know, consideration for inspection, I'm assuming part of it.
So yeah, it's the inside of the tower legs and the inside of the tower head are open. So on the screen, the pea green color is open, and there's an elevator in the leg that gets you up to the point where the legs come together, and then there is ladders and platforms in the tower head that at each of the levels where the stay cables come in. So everything inside is accessible for inspection, maintenance activities, or whatever the case may be once the bridges go into service.
Okay. Good. Yeah, obviously we gotta maintain it and watch everything that's going on. So I guess there's a variety of other little questions here, and a lot of them all come back to, I think you addressed them during your presentation. One of them was that you know, what was the total cost? And I think you mentioned that at the beginning.
Yeah, it's around 6.4 billion. Yeah,
6.4 billion. Canadian or US dollars?
Sorry, Canadian. Yeah, Canadian. I think you guys do the math divided by 1.4, 1.38, so whatever.
Yeah, well, a great presentation, guys, and great project. And like I said, really looking forward to driving it someday. So thanks. I'll turn it over to Adirad.
Thank you to all the speakers for it. Wonderful presentations and very interesting, very complex again. So also again, one more time, I know many of you are planning to attend the 2026 World Bridge Engineering Conference. The deadline to submit your abstract is May 25. So you still have time. And we hope to see many of you at the conference. Please mark your calendar and attend the conference. So on that note, we will conclude our webinar today. Thank you.